Hi everyone, welcome back to my channel. This is your Professor Hare Krishna, and in this session we shall learn about the derivation of Gibbs phase rule. So in our previous session of phase equilibrium, we have given the mathematical form of phase rule, that is F is equals to C minus P plus 2, which was actually proposed by Gibbs. And in this session, we shall see which are the conditions that Gibbs considered and which are the factors that has been considered in order to derive the phase rule. And now we shall directly enter into the concept. And here we have given a system which consisting of components C1, C2, C3 up to component C, which are distributed in the phases alpha, beta, gamma, delta up to P number of phases. So as a whole, we can say that the system consisting of a total of C number of components which are distributed in P number of phases. And you can notice over here, if you consider the first component, that is C1, which is distributed in the phase alpha, beta, gamma, delta in all the phases, I mean to say each component C1 is distributed in all the phases. Similarly, the component 2 is distributed in all the phases, as well as the component C3 and the C component. Means all the components were distributed in all the phases. So you can say the component 1 is having passage from one phase to another phase. So here component 1 is passing to beta phase from alpha phase, and again from beta phase component 1 is passing from gamma phase to delta phase up, and as well as in P phase. And this passage of component from one phase to the another doesn't constitute a chemical reaction, that you can notice over here. In all the cases we are exhibiting the component as a C1 only. There is no changes have been observed and it has been notified. So the passage of component from one phase to the another phase doesn't constitute a chemical reaction. And in such a case, in order to define the state of a system, or else the state of each phase of the system is completely specified, or in order to specify the state of this particular phase with respect to component C1 or with respect to component C2 or with respect to component C, we have to define the system, and in order to define the system we need to specify the variables. And here, in order to state the phase of a system completely, we need to specify two variables such as temperature and pressure. So we are in need of two variables which are supposed to be specified in order to define the system. And along with these two, we need to say about composition of each phase. Composition of each phase. So the total number of variables that are in requirement for defining this whole system can be given as, that is, total number of variables that are supposed to be specified in order to define the system will be product of number of components and phases plus the two variables, that is temperature and pressure. So the total number of variables required will be Cp plus 2. Let me consider this as equation number 1. And here we said the composition of each phase is supposed to be specified. That means composition of a particular component in all the phases is supposed to be specified. So here in this system we have taken more number of components. So the composition of each phase with respect to individual component. I repeat, the composition of each phase with respect to individual components should be very small, will be in a very small quantity. So we need to express the composition or concentration of the phase in terms of mole fraction. So the composition of each phase can be expressed in terms of mole fraction, that is chi. So composition will be expressed in this way. So composition of the first phase, that is alpha phase, will be given as, so composition of the alpha phase with respect to component 1 will be taken as x1 alpha. chi1 alpha, and composition of the alpha phase with respect to second component will be x2 alpha. Similarly, composition of the C3 component with respect to alpha phase will be x3 alpha. Like that, composition of the C component with respect to alpha phase. So this is the composition of alpha phase. Similarly, we can say about the composition of the second phase, that is beta. So in the same trend we can follow. So chi 1 beta, chi 2 beta, chi 3 beta up to chi C beta. So this is for second component. Similarly, we can write for all the components, and at last composition of the first component in P phase, composition, that is mole fraction of the second component in P phase, as well composition of third component in P phase, and composition of the C component in C phase. So this is the composition of each phase with respect to all the components present in a system. We know that if you are expressing the concentration of a particular component that are present in a system in terms of mole fraction, we are well aware that the sum of mole fractions, that is, if the system is having only two components such as A and B, if the mole fraction of component A is chi A and mole fraction of component B is chi B, the sum of the mole fraction, that is chi A plus chi B, will be always equals to 1. In the same way, the sum of mole fractions of all the components will always equals to 1. So that we can say in this way, the mole fraction of the first component in alpha phase plus mole fraction of the second component in alpha phase plus mole fraction of the third component in alpha phase, so on, mole fraction of the C component, or else let me write in this way, the sum of the mole fractions of the first component in all the phases will be equals to the sum of mole fractions of the all components in beta phase, that is chi 1 beta plus chi 2 beta plus chi 3 beta plus so on up to C number of component. That will be equals to say mole fraction of first component in P phase plus mole fraction of second component in P phase plus mole fraction of third component in P phase, so on. That whole thing will be equals to 1. Right. So according to the condition, sum of mole fractions of all the components present in a system will be always equals to 1. So that we can write in this way, summation of, with respect to I number of particles, the summation of mole fraction of I number of components present in P number of phases will be always equals to 1, provided I will be 1, 2, 3, so on up to C number of phases. So this is the condition we have said with respect to this one, that is sum of mole fractions is equals to 1. And you can notice over here, for the alpha phase we are having an individual equation for the mole fraction. For beta phase we have the individual equation, and for for alpha phase we have the individual equation, for beta phase we have the individual equation, for gamma phase we will be having individual equation. Similarly, for P phase we are having individual equation. So for all the P phases, if you consider it separately, there are P number of relations of this particular type we can write. Right. So that we can say for all P number of phases that are present in a system separately, for each one, for each phase, there will be P number of relations with respect to mole fractions. But here we can notice that in the pictorial presentation, in the diagram what we have given for mentioning the number of components and number of phases, the distribution of the component between two phases is existing in the state of equilibrium. That means the distribution of each component will be existing in the state of equilibrium between the phases. And here you can see between these two phases there is one equilibrium reaction, this one. And between beta and gamma, this is the one. Between gamma and delta, this is the one. So if you consider only these two, between two phases we are having one equilibrium relation. Between these two phases we are having one equilibrium relation. Between these two phases we have one equilibrium relation, right? So between two phases there will be one relation that we can be given. Right. So in order to express that equilibrium, we should well aware of the chemical potential of each phase. Chemical potential in the sense, if you consider a species present in a system, the energy that can be absorbed or released due to the change of particle number of a given species will be called as chemical potential. I repeat once again. For a species in a system, the chemical potential is the energy that can be absorbed or released due to a change of particle number of the given species will be called as chemical potential. So the chemical potential of the system is supposed to be mentioned since the components are present in the state of equilibrium. So, if you consider the state of equilibrium, at equilibrium, the chemical potential of each species must be the same in each phase. I repeat, at equilibrium, the chemical potential of each species, that is with respect to each component, potential of each species or component must be the same in each phase. There should be no change in the potential of the component. So as you have seen in the diagram, so what is the number of components are there in alpha phase? The same number of components are there, same number of particles are there in beta phase also. There is no change in the potential. There is no change in the number of particles. Means the chemical potential of each component is same. If there is a change in potential, if there is an absorption of energy, if there is a release of energy, then there occurs variation in the number of particles of each component. But here in the picture we have seen that there is no change in the particle. That means even though the component, that is C1, C2, C3 or whatever up to C number of component, when it is passing from one phase to another phase, the chemical potential of the component is not changing. So the number of particles of each component remains the same in all the phases, even though it is passing from one phase to another phase. Say if you consider mu is the symbol for chemical potential. The chemical potential of the component 1 in the alpha phase will be equals to the chemical potential of the same component 1 in beta phase. There is no change in potential at all. Similarly, the chemical potential of the component 1 in gamma phase will be equal and up to the chemical potential of the component in P phase. Similarly, the chemical potential of second component in alpha phase will be equals to chemical potential of the same component in beta phase, potential of the second component in gamma phase up to chemical potential of second component in P number of phase. So this will be continuous. For all the components we can apply the same condition. Okay, so with this particular relation, we can say that at equilibrium, there will be no change in the number of particles of each component. The number of particles of individual components remains the same, even though they are passing from one phase to another phase. So in the diagram, you can see, as earlier said in the last minute, so if you consider the equilibrium between the C1 component between alpha and beta phase, we will be getting one relation, equilibrium relation between these two phases. And if you consider three phases, say alpha, beta and gamma, in which the C1 component is distributing, so here is one equilibrium relation and here is one equilibrium relation. So totally two equilibrium relations we are having among the three phases in which the C1 component is distributing. So in how many number of phases the component is distributing, the number of equilibrium relations will be one number less than the number of phases in which the component is distributing. So between the two phases, the number of equilibrium relation is 1. Between three phases, the number of equilibrium relations are 2. If the component is distributing among the four phases, the number of equilibrium relations are 1, 2, 3. So hope you understood. So as a total, we are having P number of phases in which C number of components are distributing. I repeat, among the P number of phases, C number of components are distributing. So the number of equilibrium relations that can be developed between the components, between individual type of components, between the two phases, between the phases will be taken as C number of components are there and they're developing. There are a total of P number of phases and P minus 1 number of equilibrium relations have been developed, right? The same condition we can consider, that is, there are P minus 1 number of separate equations for each component, and hence for a C number of components, the number of such equilibrium equations will be equals to C of P minus 1. And since we have seen between the distribution between two phases, the distribution of each component is existing in the state of equilibrium, and at equilibrium there will be no interaction between the number of particles of the components between the two phases. So the chemical affinity between the components, between the particles of components present in two different phases will be always 0. There is no interaction at all. So if AF is the chemical affinity, then for I number of particles, the whole and sole chemical affinity will be equals to 0. So AF is the chemical affinity for I number of components. Okay, so I will take the values 1, 2, 3 up to R dash. So here R dash is, there will be totally R dash number of equations that are showing 0 chemical affinity. So AFI is the chemical affinity. At equilibrium, the chemical affinity will be equals to 0. Okay, so for R dash number of equations that are showing 0 chemical affinity, will give some restricting conditions for the variables to specify or to define the system. So for R dash number of equations, the total number of restrictions, the total number of restricting conditions or total number of restrictions for defining the system by using the variables temperature and pressure will be given as the total number of restrictions will be for P number of phases having C of P minus 1 equilibrium relations, having R dash number of equations possessing 0 chemical affinity. So this is considered as equation number 2, which gives total number of restrictions. So our main intention is to obtain the number of degrees of freedom, that is F. So the value of F, that is number of degrees of freedom, will be always equals to the number of variables which are using in order to define a system minus the total number of restrictions, for defining the system. So how much of variables we are using for defining the system minus total number of restrictions imposing in usage of the variables for defining the system. The difference between these two things will give the value of number of. So As we said, the number of degrees of freedom will be equals to the difference between the number of variables which are used for specifying the system and the total number of restrictions that are imposed due to their interdependencies. So the number of variables that are used for defining the system will be given in equation number 1 as total number of variables is equals to Cp plus 2. And the number of restrictions have been given as p plus c of p minus 1 plus r dash. So we can use both these equations in order to calculate the number of degrees of freedom. So the number of variables were equals to Cp plus 2 minus of total number of restrictions are p plus c of p minus 1 plus r dash. So on doing the simplification, you will be getting Cp plus 2 minus p plus minus Cp minus c plus r dash. So you will be getting plus c. So plus into minus minus, minus into minus, you will be getting plus. Okay. So here plus Cp minus Cp will get cancelled and the remaining things will be C minus P plus 2 plus R dash, and that will be equals to F. So we got F is equals to C minus P plus 2 plus R dash. If you consider the system is non-reactive in nature, that means if no reaction is taking place in it, then the equations of the type, that is AFI is equals to 0, that is the unaffinity, chemical affinity is equals to 0, that what we have taken will not be present. So in that case, the condition R dash will be equals to 0. So for the non-reactive system, for a non-reactive system, the term R dash will turns to 0. R dash will be 0 for a non-reactive system. So if you consider this particular thing, and if you impose the same thing in this equation, the whole term will turns to 0 and remaining things will be F is equals to C minus P plus 2, that what we call the phase rule, which was proposed by Gibbs in order to calculate the number of degrees of freedom by knowing the number of components and number of phases in a system. And now we shall solve one or two problems based on this phase rule proposed by Gibbs in order to calculate the number of degrees of freedom that can be used, that should be used in order to specify a system. So now we have the equation for Gibbs phase rule, that is F is equals to C minus P plus 2. By using this mathematical formula, we shall try to calculate the number of degrees of freedom by knowing the number of components and number of phases that are present in a given system. So here is a problem. So we need to calculate the number of components as well as the number of the degrees of freedom in our first problem, that is an aqueous solution of glucose. So in this case, you can give a clear notice, that is an aqueous solution of glucose. Glucose is soluble in water. So we will be getting a homogeneous phase. That means we can't judge the particle of glucose and a particle of water as distinct parts. So we will be getting a complete homogeneous mixture of glucose and water molecule, so that the number of phases is appear to be 1. Okay, and now we need to get the number of components in a system. For calculating the number of components, we can go with the individual chemical composition. So water is a distinct chemical composition and glucose is a distinct chemical composition. So the number of components will be equals to 2. And we can calculate the number of degrees of freedom, that is F is equals to C minus P plus 2. So the number of components are 1, and then the number of components are 2. The number of phases are 1 plus 2. 2 plus 2 4 minus 1. So number of degrees of freedom are 3. So the system is trivariant. Means we are supposed to specify 3 variables in order to specify the system. So the 3 variables will be temperature, pressure as well as the concentration. So these three parameters we are supposed to use in order to specify the system. So now we shall consider one more system. So this is the second system we are having. The system consisting of CaCO3, CaO and CO2. The reactive system it is. So for a reactive system, as we said, in order to determine the number of components, we are supposed to go with the simplest equation, that is N minus E, where N is the number of constituents present in the system and E is the number of independent equation. So for these components, we can write the independent equation as decomposition of calcium carbonate to give the quicklime, that is calcium oxide with the liberation of carbon dioxide in gaseous state. Quicklime is in solid state, calcium carbonate in solid state. So totally we are having one equation and three components. So 3 minus 1. So the number of components equals to 2. So number of phases will be, since if you consider this particular equation, the number of phases will be calculated in such a way. The number of phases will be equals to 3 over here, because this calcium carbonate is physically distinct from calcium oxide. Though they are present in the same physical state, they are physically distinct. So this is one solid phase, this is the other solid phase, and this is the gaseous phase. So totally we are having 3 phases. So the number of phases in this system will be 3. And now we can use the mathematical formula, that is Gibbs phase rule, that is F is equals to C minus P plus 2. So here the number of components are 2, the number of phases are 3 and plus 2. Right. And if you do the calculation, so 2 plus 2 it is 4, 4 minus 3, 1. So the number of degrees of freedom for this particular system is 1. So it is monovariant system. So only one variable is need to be specified in order to define the system. Either we can use temperature or we can use pressure. So either of one parameter, either of one variable can be used to define the system, so as to one of these two parameters is supposed to be specified in order to define the system. Like this, we can use the Gibbs phase rule in order to calculate the number of degrees of freedom, and we can say to what category the system will belongs to, that is whether it is invariant, monovariant, trivariant, divariant, and the factors or the variables that are required to define the system. All these things can be calculated by using the phase rule. And that's about the derivation of the phase rule and the usage of it in calculation of number of degrees of freedom. So if the video is useful for you, please like it, share it, and do subscribe to my channel and press the bell icon so that you will get the notification for any update in my channel. Thank you.